So I appreciate this discussion on how to grade. I want it to feel fair. And like Matt said, I'm going to clarify in the unit test problems and on the exam problems, not just how many points a problem is worth, but where those points are coming from. It might be challenging to get the wording down at first, like in a synthesis. If I say it's 6 points, 3 from the reagents, 3 from the intermediates, other sequence and plausibility, or like if correct but plausibility is wrong, 3 points, it's going to look a little awkward. And I'm not trying to say I'll take off more than points possible, but there's a lot of factors that go into these problems that make them really challenging to grade. And some of those factors are you've got the steps right, but there's things inside of them that are wrong. Ultimately, though, I'm going to work to give you guys feedback. Actually, that's one of the reasons I stopped doing midterms. I stopped doing 3 midterms and went to 1. And it's the reason I started doing unit tests. It's because I never had an opportunity to give feedback to my students. I was only grading homework and saying yes or no, you did it right, and grading exams saying yes or no, you did it right. On unit tests, I get a chance just on part B to zoom in and say, here's what you're doing right, here's what you're doing wrong. It's targeted feedback. That's my goal with the unit tests. And I think I've been seeing improvements in my classes because of that targeted feedback, but I want to continue making the grading more logical. All right. We're going to dive into Unit 3, which is on alcohols and ethers. But actually, before we dive into it, we're going to take kind of a tangent that plays a very important role in section 17, alcohols, and that is organometallics. That is some carbon group bonded to a metal. To be fair, people will argue that it doesn't need to be a carbon that's bonded to a metal. It needs to be some organic molecule that's bonded to a metal. For instance, my graduate work and my undergraduate research work were on metal organic frameworks. So those are kind of organometallics. But the most interesting thing here is when a carbon is bonded to a metal. You may have previously seen when we take something like acetylide and we react it with sodium hydride, we get this sodium to carbon bond. Textbooks will sometimes say, this is an organometallic, despite the fact that that bond, you would never look at it and say that's covalent. You would look at that bond and expect it to be metallic. In the same, ionic. In the same way that you would expect NaCN, sodium cyanide, to be simply ionic and not covalent. So I don't like this. Some textbooks say that sodium acetylide complex is organometallic. I don't know that I agree with it. But here are 3 new classes of organometallics. The first, and probably the most famous, those of you that were in lab have already synthesized and used this. Anyone other than Alex know how to pronounce this name? Greenyard? Grignard? Grignard. It's actually pronounced more with a Y sound. Grignard. What language? I don't know. It's a name. What isn't? So I'm not going to be pronouncing it as Grignard. If you get confused about what I'm talking about, we're talking about Grignard. I apologize for my handwriting. That looks like an N before the D, but that's an R. Grignard. The generic form of a Grignard is carbon bonded to a magnesium halide. And it is drawn like this, with a covalent bond between R and Mg. Could you come up with a better name for that generic complex than Grignard? Cooper, what would you come up with? Just off the top of your head. Keep in mind, it's a type of organometallic. What do you want to clarify about this organometallic? But you didn't put organo in there anywhere. Organomagnesium halide. Yeah. That's what I would call it too. Because that's what it is. Yeah. So you could call it a methyl magnesium halide. Methyl magnesium bromide. Yeah? You could have phenyl magnesium chloride. Those would be like systematic names for them. But common names, methyl Grignard, phenyl Grignard. Yeah? The next class is called, you're never going to believe this, organolithiums. No one claimed it. What'd you say, Maddie? Wow, that's a really funny sounding last name. What language is that? And no one will claim it, ever. Organolithiums, what's their generic form? RLI. Do you wonder why the organolithiums don't need a second ion like the organomagnesium halides? Lithium is +1, magnesium +2. What does that mean about the charge of carbon here? It's a -1. And you might think of it as this partial negative with a partial positive on the metal. Although for almost all of these, you can think of them as almost basically ionic. Their bonds are actually this weird place where they behave somewhat covalently, but they also behave somewhat ionically. Do you know what the difference is between a polar covalent bond and an ionic bond? Whether or not there's a combined orbital? Touching orbital? That would be a really good way to look for it. Hard to experimentally prove. And that's not the definition. No. I would say that would make a good definition if their orbitals overlap somewhat. It's covalent on some degree. If their orbitals don't overlap, it should be ionic. But that's not the definition that we teach you in Gen Chem. The definition is a line in the sand. It is, if the electronegativity difference is greater than 1.9, ionic. If the electronegativity difference is less than 1.9, polar covalent. That's what differentiates an ionic bond from a covalent bond. We differentiate it. We came up with those terms. We apply it. So it is a little bit weird that these bonds are kind of covalent, kind of ionic, but that's because we're trying to fit nature into our little abstract boxes. In the same way that we can have methyl Grignard, we could have something like methyl lithium. One of the most common organolithiums is called inbuli. N there, do you guys know what it stands for?
Nitro?
Not nitro. This is like S and T. S for sec, T for tert, N for normal. So N-butyle is this compound. S-butyle would be if it came off of one of the secondary carbons. And of course, tert-butyle would be if it came off of the tert-butyl group. N-butyle is one of the most common organolithium reagents. It's an incredibly strong base. There's one more type of organolithium, but I want you to think about organomagnesium halides and organolithiums as being one family, and this other type of organometallic as being its own family. And we'll actually make sense of why they're different families. I can do more than just put a box.
What was the distinction between the previously versus now?
Some textbooks will tell you that this is an organometallic.
Is it?
I don't agree with it because its behavior is not as characteristic as the rest of these. I mean, it is an ionic carbon balanced by a sodium ion, but it's just not quite the same. This last family is called they have two names. Gilman reagents. And actually, I'll show you what the structure looks like before we make sense of a more systematic name for it. The Gilman reagents have two equivalences of an organo group bonded to a copper, and that's copper 1+, copper 1, not copper 2, copper 2+. Because that's copper 1 balanced by two R groups, it's also balanced by a lithium ion. This has net negative charge. So we can actually abbreviate this. We write it as R2CuLi. So I think that technically the best name for this would be lithium diorgano cuprate. Cuprate is probably not a term that you would have picked for this. That's okay. I want you to learn that as a familiar word. Cuprate probably still should make you think of copper. You can actually see the Cu of copper in cuprate. Latin name. Cooper.
I have a question. So maybe we'll cut this, but these R groups, so you said them as R. Are these the same R groups, or could they be different R groups?
Here, they should be the same.
Okay.
In synthesizing a Gilman reagent, you typically only have one R group to work with. Good question. Now, when I name this, I don't necessarily like to name the lithium. So I will often refer to this as a diorganocuprate. And I expect you to know that it's balanced by lithium. But there are some people that don't like to spend the time saying a diorganocuprate, and so they just call them cuprates. In my opinion, any of these three names do a better job at describing what the complex is than Gilman's last name. Sue me. Don't sue me. I will start calling it Gilman forever, I swear. Why is it that this is its own family?
So the R's are identical?
Yeah, they'll be identical in all of the applications that we use it in. We're going to deal with these three organometallics. Grignards, organolithiums, and cuprates. What distinguishes the cuprate from this other family? So I heard copper, two metals, occupies d orbitals, free-floating lithium.
Double ionic bond.
Double ionic bond. Actually, it's not double. It's not ionic. This is
Copper covalent.
this is more covalent than this, and it is because of the d orbitals. These are main group elements. So if you don't want to just call these one family, then you can recognize that these are main group metals. That's going to give us different chemistry. This is a transition metal. And transition metals pretty much have their own chemistry class surrounding them. And guess what? We are not in that chemistry class. We are in organic chemistry and not inorganic chemistry. But many textbooks these days are teaching a lot of the principles of inorganic chemistry. How this copper is actually bonding in this in these types of reactions. It goes really in depth, and we won't have to.
So are cuprates what come from transition metals or copper specifically?
Just copper specifically. Good question. Cuprates are just with copper. Now, I'm not saying that that's the limit of all organometallics in the world, but that's what we're going to cover. These are the most famous organometallics. And the things that the main group metals allow are not always the same as the things that the transition metal will allow. These can run all of the same reactions. Anytime you see a reaction that uses a Grignard, could have been an organolithium. Just depends on whether you want to work with lithium or magnesium. But anytime you see one of these, you may or may not actually be able to use a cuprate for it. And there are reactions that cuprates can do that these reactants cannot do. Incapable of it. So, to dive into this, we're going to look into the synthesis of these organometallics. The generic synthesis for the Grignard, alkyl halide, reacts with magnesium to make organomagnesium halide. I have explicitly put Mg0, but you will not always see Mg0. Sometimes you will just see Mg. How are you supposed to know the charge on Mg? No charge is written, and it's not bonded next to something. It's not bonded with an atom. That is elemental magnesium. Many places will also add this in. I'm not often going to add this in. They will say THF, or they will say generically ether. And there is a reason for that. We're going to get into it. These reagents are incredibly strong bases. If there is anything slightly willing to give up its hydrogen, this reagent that's formed will take it. So you need something inert, like an ether compound. In lab, what ether did you guys use? Diethyl ether. THF is tetrahydrofuran. That's the reduced brother of furane, the aromatic ring. It's just an ether. But again, I'm not requiring you to put these. And you often won't see it from me, you'll just see magnesium. All right, so let's do some practice problems. Show me the product formed here. Show me the reagent needed here. Give me the reagent over that one. Is it missing something? Yeah, the starting material. Oh. I don't know what you're talking about. Yes, there is.
I was like, how do you get magnesium by itself?
Thank you for that.
So,
No, it's okay. I'll get it. Oh, it actually came out.
well, is copper plus 1 there? There? And then the two R groups make it minus 1?
Yep. Exactly that. Anybody feel brave enough to put their answer on the board? Feel free to claim any of them.
That one, do you want us to do like DHF or ether?
Don't need to. You don't have to. That's why I put them in parentheses, which is to say you'll see that, but it's not required. First come, first serve.
Magnesium, I guess.
Oh. This one's dying, so it doesn't look good. We can give you a different one. Good work. So, in the first reaction, we get methyl Grignard. You will most often see chlorine and bromine as the halogens here. It's less often you would see iodine, and I don't know that I've ever seen fluorine written in a Grignard. For my class, it's going to be bromine and chlorine. The easiest thing there is you just insert magnesium between the carbon group and the halogen. Reversing the synthesis, identify what halogen is written, remove the magnesium, and bond that halogen back to the carbon. I want you to notice, what is the hybridization of the carbon in the first step, in the first reaction?
SP3.
sp3. And in the second?
SP3.
sp2.
And P.
This carbon here is an sp2 carbon.
Oh.
I meant the relevant carbon that's reacting to become the Grignard. And part of an alkene. And here, sp2 and part of an aromatic ring. So Grignards are not reserved for any specific type of carbon. It is rare that you would see a Grignard on an sp hybridized carbon, the acetylide, right, on the end of an alkyne. That's because it's rare to see an alkyne that bonds to a halogen anyways. So I want you to recognize this will happen on both sp3 and sp2 carbons. The stereochemistry of the alkene doesn't change. I'm not going to ask you guys to show a mechanism for these reactions because the mechanisms are not very well laid out in any textbook. But I do want you to recognize that the magnesium has 2 valence electrons. I mean, I've drawn them as 2 separate dots there, but we know they're both in the S subshell, so they may act as a lone pair. This, again, is what's unclear. Do they act individually as radicals, or do they act as a lone pair? Now, we know that when a bond breaks, like the CBr bond, those electrons are owned by the more electronegative atom. So bromine should be taking these electrons, which means that magnesium is donating its electrons to the carbon. So you might think of the transition state here, where the bonds are forming and the bonds are breaking, as looking something like this. If you remember anything from OChem 1, the stereochemistry of this doesn't work. The orbitals don't work. This looks almost like a backside attack, but it's not coming from the backside. So maybe then we have to reconsider our mechanism, and I apologize, I know some of you guys are writing this down. In that maybe the mechanism is more like 2 radical reactions, where the magnesium donates 1 electron to the carbon, and carbon takes 1 of its bonding electrons for the magnesium, and the bromine takes the other bonding electron and takes 1 electron from the magnesium. In which case, we get a structure that's more like magnesium is getting pulled into the bond. Magnesium is being sucked in between the carbon and bromine. That wouldn't break any orbital rules and would allow the stereochemistry to be preserved. You guys see this, right? How it has a specific orientation in the starting material and the product. It's not flipping anywhere. That pi bond's not really allowed to flip anyways. It's too high of energy.
So then why is it like an unsure thing? Is it just you can't decide?
To be fair, I'm unsure. I'm not sure that all of the scientific community is unsure. This is one reason I'm not asking you to show the mechanism though, because 1, it's not very intuitive or helpful. And 2, it's not covered in your textbooks. So if you didn't understand my explanation, you'd have to try and go get somebody else's. So it's for this reason, no testing on the mechanism. Why am I showing it then? Because I get students every semester that say, but can you just show the mechanism because I don't understand it? You won't understand it. It's not gonna help. All right, guys, let's take a break. Why don't you get up, stretch your legs, get your blood flowing, and we'll come back in to look at synthesis of the others and reactions they can do. In that break, I'm gonna go get blue and black pens. They're running out.
What is this?
Would I be open?
Maybe. I don't want to be that guy though.
You have questions for me? What's up?
How is ACF?
It's been a mess.
Has it?
Yep.
Like just with events and stuff? Or?
Yeah. That was. Ugh. Like I like hit conflict. Oh man.
I'm sorry, dude.
No, you're good. It is what it is. I'm working on ACS stuff right now, trying to get access to oil sets for that submission project.
Oh, nice. You guys have any events coming up soon?
National Chemistry Week is in like 2 weeks.
Or? Oh, nice.
So we have a different thing going on each day.
Wonderful. Keep around. Is it just you're at Slick?
Yeah, it's just here. It's like, it didn't go through.
But it didn't go through. Like not even like with just beeswax.
No, the abstract didn't get submitted.
Wait, what?
Emmanuel.
Oh, he said that.
Alright.
Why? Because he still thinks we're using his intellectual, because there's still concerns of his intellectual property being used. Or at least, I don't know, I haven't had a conversation with him, but yeah, no, it didn't work out.
Oh, that's too bad. I'm sorry.
I apologize.
Literally keep
The
on
other
saying
like
that.
homework problems, like the hard ones that I scared of, and just worked with
Now, they're already using
Johnny.
something else with
And then I got like that
the
same problem.
GCMS and stuff.
Oh, is that what that?
Like, I don't know.
Yeah.
That was about.
Yeah, that's it.
And just the fact that you use notes.
That's
If
what
you
they
use notes,
do.
I mean,
I
that's
think
still, to be honest, that's probably better for their resume than long text project. Because you can show like I have experience with all this instrumentation and I know how to use it and I have proof that I know how to use it and
Oh, no, it's really frustrating that at the very last minute, he's just like, yeah, like, just don't, and I'm just like, son of a bitch. Yeah,
yeah, no, that is frustrating. I'm sorry.
I tried having a conversation with him, but he didn't have but he had to finish out the last year, so it's like, now it's just like, everyone's so stuck on his head, it's like,
Yeah.
I am right though. He's like,
That's tough.
because
it's really funny because
remember
when,
if I don't
as like,
survive,
yeah,
yeah, you know what I mean.
As far as
Oh,
this is concerned,
like,
that is fine, but the
yeah,
next.
I don't know about that.
No, not that's just
So,
No, you're good.
reaction,
yeah,
unless
we're
we
good.
I don't have my grade for part B yet.
So maybe this was probably just really short notice too, and like maybe just
I
get
hate
this
when I'm like, so I was glad to see
doing
you
that
just
kind
do
of
it
overview
instead.
of the project.
Like, your class or
Rob or something.
yeah. Like, and then
I know that I guarantee you there's none of this intellectual property.
and then like for
Yeah.
things where I'm like, I want to like.
That's the most frustrating part
reference
is
it a lot,
I don't know how he got that idea.
Yeah,
well,
that is true. Yeah.
I'll
But
just make
literally
it
the only
its
thing
own
that I said I
standalone
talked to him about is
thing.
just a couple
So I have
conversations.
to like scroll between the two.
Yeah.
I'm like, I need both of these.
In
You
class
know?
when we talked about this.
Mhm.
That's it. That's not necessarily intellectual property.
Yeah.
So I'll talk to him more about it, but
I'd rather have
no,
that
I'm
than
really
be like
frustrated
searching
that
through one.
didn't go through.
Yeah, I'll I can also talk to him too and see what is going on. Or what his thoughts are. But yeah, I'm sorry. Sorry to hear that.
No. Yeah,
Yep,
so
already.
that's part of what. Yeah, no, I was not happy about that. I was just like, it's not even my project. It's just something I wanted to get started just for the represent biology.
Well, you know, kind of.
Okay.
Well, you know.
Do you get to think on that transition state? Does it make more sense to you now? Or are you glad you don't have to show that mechanism? Good, good. All right. Let's show the synthesis of organolithiums. Do you suspect a starting material? What would you suspect it would be?
Butane?
Did I say something wrong? Organolithiums is what we're showing next. Is that what I said?
Butane.
Okay, thank you.
Butyl? BU?
So you think we would start with just R?
Oh, it doesn't have to be butane?
No, it doesn't. I think I showed you that there's any version of an organometallic you can come up with, or a Grignard, could be an organolithium. Yes, we will need organohalides again. Rx. We already know that the product is R-Li. So what's the byproduct? No. Good try.
The
Not X2.
halide ion or negative charge. So like
Oh, I'm sorry. This isn't fair. Over the arrow, we're not going to put Li. Because you guys are coming up with really good things, but if we showed the halide ion, doesn't that make this net neutral and this makes X like net negative? Which doesn't balance, right? It's not Li over the arrow.
In acid?
It's 2 Li. That changes things. What's the byproduct now? LiX. Hop off the plane. LiX. Why do we need twice as many equivalences of lithium compared to magnesium? Charge. In the same vein, can you finish that thought? What kind of is determining the charge that lithium and magnesium take on? Beautiful. Valence electrons. Magnesium has twice as many valence electrons. Lithium has half as many. And we're still doing a 2-electron reduction to carbon. Carbon gets to keep one of the electrons from its bond to the halogen. It gets to take one of the electrons from the metal. This metal only gives 1 electron, so we'll need 2 of them. So let's do some practice, right? Let's show this in application. Here is N-bromobutane, 2 equivalences of Li. Predict the product. Show the product, show the intermediate, show the reagent, excuse me. Show the starting material.
Are these reactions still affected by like electron donating groups and withdrawing groups in benzene?
Okay, so a good question. We will actually get into limitations around these reactions, which is these are incredibly strong nucleophiles and incredibly strong bases. So if I have a carbonyl on a ring and I create a Grignard, I risk 1 molecule of that Grignard, or organolithium, attacking as a nucleophile the carbonyl of the other molecule next to it, and kind of causing like a polymerization reaction. So we have to have some control in what groups are on the structure when we do these reactions. Yeah? But no, to my knowledge, I don't know that electron donating or electron withdrawing groups,
So like the
they likely
position
do
where-
have some change on the rate of this reaction, but not one that's like
So, like,
important.
like the directors and stuff. It doesn't really.
No, you won't have to worry about that. Like, is it gonna turn the ortho halide into the Grignard, or is it gonna turn the meta halide into the Grignard? You won't have to worry about that. Ortho, para, meta directing, we'll leave that in EAS and NAS reactions. Well, who wants to put some up on the board? Feel free. First come, first serve. Got brand new black here. if we can get a different set of 3. There we go.
Polymerization.
Poly means many. Mer means unit. Ization means get it done. Yeah. So polymerization is making many units.
Are they connected?
Connecting many units. Getting many units done.
Oh, so they're still bound to the carbon. They just connect.
Sure. Polymers don't necessarily have to have carbon, although that's pretty common.
I meant.
So like monomer is 1 unit. Dimer, 2 units. Polymer, many units. All plastics are polymers. So like polyvinyl chloride, you take vinyl chloride and you polymerize it. You turn 1 unit into many units. All right, let's see what we got. N-bromobutane, 2 equivalences of ionic lithium, elemental lithium. So just like last time, it's very common to see an ether written under the reaction arrow, although I'm not asking you to provide that because if you ran it in water, you wouldn't live to see another day anyways. Just kidding, I would never let you run this in water. That's why. N-bromobutane, 2 equivalences of elemental lithium, and we get our reduced carbon. We get N-butyl lithium.
Is this the same as excess lithium?
It's not excess lithium. You might want it to be in excess, but you might not want it to be in excess. Lithium is just not something fun to work with in a lab setting. So I think that if you were running this yourself, you'd probably try to match equivalences pretty directly. Magnesium, on the other hand, nothing. You can run magnesium in excess for sure. And we've got our byproduct, lithium bromide. Down here, we're converting this allylic chloride. You guys remember what allylic means? Adjacent to the alkene. This allylic chloride goes to this allylic organolithium, and then of course we've got that byproduct, LiCl, lithium chloride here. And then the bottom, we had this para-substituted organolithium anisole, organolithium methoxybenzene. So I think we could call it para-methoxy phenolithium. Did it have to be bromine in the starting material? No, could have been chlorine. I also would have accepted iodine, would work great. And so the byproduct, since you chose bromine, the byproduct becomes LiBr. Good work.
So do you just like mix them all together and put them under a flame?
Put them under a flame.
Or just put them in a beaker, heat them up. That's how you do the reaction.
Yes. Did you go to lab when you ran the organometallic
Yeah.
synthesis? Great. That's
It's
how
the
you
same
do
for
it.
all of them.
Mm-hmm. All right, our last organometallic synthesis of the Gilman reagent. This one will blow your mind. We don't start, didn't blow Brett's mind. You watched last summer's videos this morning. We don't start with an organohalide. We don't start with an alkyl halide. We start with an organolithium.
Don't you need 2 RLI?
Good. So this is the confusing part in the way that it's written. You need twice as many equivalences of the organolithium as equivalences of cuprate you want to make. What is the byproduct in this step? One more time. Not just iodine. You good. Lithium iodide. LiI. But many places that you see this generic reaction will not say it as two equivalences of organolithium. Because oftentimes the organolithium is something that you are synthesizing directly anyways. So you say, for every equivalence of organolithium, you need half an equivalence of copper iodide. Isn't that the worst? I don't like it either. Here's what I'm willing to do with you guys. You won't have to specify equivalences during the synthesis of the cuprate. Synthesis of organolithium, yes, I do expect you to show that because that's almost always an easy win. But here, especially if it's like part of a multi-step synthesis, which by the way, one of your Unit 3 Part B questions is a multi-step synthesis. You get one, solve the synthesis, excuse me. You get one multi-step and one roadmap. Several steps where there's just a few blanks in them. So it's a little bit easier than just a multi-step synthesis. If this were in a roadmap, I would not require you to show the equivalences, because if you know the reagents, you've got it. I just don't care for you guys to write 0.5. It looks silly. And to that point that Killian brought up earlier, couldn't we just put copper iodide in excess and have a 1-to-1 ratio? Yes, you could. There wouldn't necessarily be a harm in that. And maybe there would be a harm because, like I said, copper is a transition metal, so it's actually doing a lot of stuff with its d orbitals that the other metals are not doing. So if you don't use all of the copper, maybe there's issues. I haven't used Gilman's reagents enough, so. All right, some synthesis. Here's what I want you guys to do. I want you to take one propene and through a series of steps, I would like you to give me oops, I lost a carbon. I would like you to give me N di-N-propyl cuprate. Haven't put my subscript. So notice that my parentheses are going through the carbon-copper bond, and I'm saying that there are two equivalences of this. Can you do it?
How do you have two? Oh, the other side?
Yeah, so I could have drawn this as copper with propyl coming off of it twice, but that is just more work and it takes up more space. So in the same way that we're saying R2, this is R, the 3-carbon chain. And it is the carbon to copper bond where this group is limited, and I want 2 of those groups. Does the notation make sense? Can you copy it? Great. Please work together and collaborate on this. When you're finished, I would like you to take anisole, and I'd like you to give me dipara-anisole cuprate. 2 multi-step syntheses. You thought I was going to go easy on you all day. Just predict the starting material, fill in the reagent. No, enough of it. Sorry. But please collaborate, talk with each other, brainstorm, work forward, work backwards, ask questions, troubleshoot, not troubleshoot. Do trial and error. Put something down, see if it works, backtrack, try something else. No. No, I'll elaborate it again. This is a good question. So this notation of propyl bonded to copper, it's like two propyl groups bonded to copper. But now that takes up twice as much space. So instead I can say I've got 3 carbons bonded to copper, 3 carbons bonded to copper twice. Okay. It's a good question. And really, like, imagine doing that anisole where we're looking at an aromatic ring. I'm sure you're not interested in drawing this out twice. And then, of course, balanced by that lithium ion. Great.
Helps me figure out how to do that.
Mm-hmm. And you know, I'd love to spend the time to tell you what copper is doing later on with its bonds, but it's just not really part of the curriculum.
How do you get a terminal halogen?
No, I did the same thing. I did for the anti-mark. That's it. There's the second one. Yeah, I know.
You're not quite right here. Missing some important piece of notation. In the final product, your product as drawn would have a +1 charge.
Oh,
Gotta tell me there's 2 equivalences total. I mean, imagine the difference is RCULI versus R2CULI. No, it's not the right reagent. Actually, this doesn't exist. Bromine doesn't like to be on its own. Br2, HBr, those exist. This actually is a reagent. If we have a dihalide, we can do a double elimination and make an alkyne. or if we have a terminal alkyne, this will deprotonate and make an acetylide ion, the nucleotide. You wanted to do this, right?
Yeah.
So tell me, what is the difference between this and this? What atoms are added? Good. That's true. So a good reagent choice might be HBr might be a good reagent choice because it has those two things we're looking for. Yeah, what do we call that? When the hydrogen adds to the more substituted carbon. That's right. And so you've got it in your review notes from the OCHEM1 reactions, but there's a reagent that can be added with HBr. And I don't want to rob you of it. Here's what I might encourage you, Jordan. Google it. Anti-Markovnikov HBr addition. Or look back in your notes and see where you wrote it before. Because one of those two things is going to help it click with you better than if I just say it. Okay? Interesting, yes. Yeah, absolutely. That's exactly where it goes. Yeah, great job. Here, though, I think it's lowercase h is Planck's constant. And it's not c. So you just turned it into h.
That's exactly right.
You feel good on the first one? Oh, but this would actually give us iodine here. So if you use H2, it returns from alkene to alkene. Alkanes aren't easy to work with. The only thing you can do with an alkane is radical halogenation, like bromine and white. And even then, the bromine goes to the most substituted position.
Yeah, you need
So we're kind of back to the What we want is this is not a bad reaction, but I need to add another reaction.
Which one did you find?
That changes how those two things act. As they add right now,
What reaction will get you the terminal hydrogen?
takes the hydrogen. That's going to put a positive charge on this compound. Where would the charge go? Go substitute. I need something that changes how the reaction proceeds, so that iodine goes up first, which means it wouldn't be a carbocation, but it'd be a radical. So we need a different reagent. You'll find it in the OCHEM1 review. Remember we did that 2 tables of
Wait. And then you just get rid of the peroxide?
You'll find it in there. Look for this.
There's got to be a quicker way than that.
Do you want me to take a look at your other one while you're at it? Sorry. Oh, you're so
You can just remove it.
Well, or you say you put in a half a foot here. So don't worry about it. No, it's okay. Actually, what I don't like is your arrow.
It's more serious.
And I think that's because you work forward backwards. But working backwards, it's how did I get 2 here? There you go. Luis, how are you feeling?
I would, they're gonna believe me when they see it. It's like, it's inexcusable.
I just added a bromine, other alkene,
And how did you decide to use that?
referred back to the chart we made.
There you go. Maddie's going to be on the same track soon. Matt, how do you
The
feel?
2 part, I like says that in this last, the diamond one.
Oh, nice. You picked
Add
it.
that on instead of the like,
No, actually, you can't. I will accept it as our Actually, one of the most common problems is
Everything's separate.
but hydrogen peroxide works super well. I would never mark that wrong because it is a valve. Great job. Yeah. This is a little bit silly because this purple is not bonded to This is an ionic. So lithium is truly just balancing. That's right. Yeah, notice up there how it's just really yeah. And here, this would work great. Perfect.
So this
Good
one,
work.
this is one way.
Yeah, did you hear about the one that went down in Little Cottonwood Canyon a few weeks ago?
Oh, I don't think they.
And there was a couple like doing honeymoon shoots, and they watched it go down.
That is actually.
No, I don't want to say any more about it because it's really sad. But there was a story about it on KSL. Great. Yes, that's exactly how you need to do that. Yep. Same here, right? Just a different item. Halogen. Do you have anything you want to show me?
There's a whoops. So there's a way to get the bromine terminal in. Oh, sorry. There's a way to get the halogen terminal in 2 steps, but I believe you can do it in 1, and I don't want to continue until I figure it out. And for the next one,
Can you say that again?
I believe you can get a terminal bromine. Oh, in a terminal bromine
In 1
only.
step.
Yeah.
Yes.
So you don't have to like have an alcohol or another oxygen.
No. Nope.
That's not possible.
You.
There's gotta be one out there.
What are you talking about? There is a 1-step direction. There is a 1-step synthesis to get that halogen on.
To get bromine and hydrogen on.
Yes. You're looking for specific regiochemistry, correct? You want the halogen here, and you want the hydrogen here. Should we solve it together?
Yeah.
All right, guys, let's go through this to wrap up our class. Now, tell me, did you do any brainstorming? Did you do any work forward, work backwards? I don't think you really had to do carbon counting for this synthesis, did you? What did you brainstorm in this first one? Or how did you work forward and backwards?
Going forward, it was how to get a terminal alkene.
So you knew that
Sorry.
you wanted
Halogen.
You knew that you wanted to get a halogen there at a terminal position, and you probably recognized that because your final complex, which, by the way, if you're going to expand it and not use the parentheses, lithium doesn't need to go with copper. It should go up above it because now the lithium is acting as an ion. You know that you want to get the bond to form here. So you want hydrogen on the more substituted carbon. What is the regiochemistry term for this alkene addition? Anti-Markovnikov. So this is where I want you to go back and review those OChem1 reactions and find reagents for an anti-Markovnikov product. Now, if you were working backwards, then you probably got to that same point because you realized I need to have a halogen here. This is the bond that I need to form. And I'm drawing a line through the bond. It's that carbon to copper bond that I want to form, which means this is the bond that needs to exist beforehand. So really, I just need those 2 steps, right? So we're looking for reagents. Let's pick a specific halogen. Shall we say bromine? I need to add H and Br. I just need to add them anti-Markovnikov. So HBr is a really good guess for this. But HBr alone would form a carbocation, acid, base, donates electrons, takes on a positive charge goes on the more substituted carbon. That would give me Markovnikov. I need a reagent that gives me different chemistry. You might not feel intuitive. That's why you need to know these and review them. I need a peroxide. ROOR would work here. A specific peroxide, H2O2. How does the peroxide change the chemistry of this reaction? Instead of a carbocation, it makes it anti-Markovnikov. Instead of a carbocation intermediate, there's what type of intermediate? A radical. Radical intermediate. What is this? Radical intermediate. And where are radicals most stable? The same as carbocations, on the more substituted carbon. And then what gets me here to this last step? CuLi, or if you wanted to say 2 equivalents of this, or if you wanted, you could say half an equivalence of this, although I would accept CuLi as full points. So 2 steps to get us there. And again, if you felt stuck here and only here, you could still get most of the points for this synthesis. You could show the intermediate that's needed and the second reagent. That's two-thirds of the points. Did you have something to add to that?
You need CUI or CULI?
Did I say CULI? I apologize. I meant CUI. Thank you. Oh, I do. I don't know who put those notes up there. Yeah, you're right. This can't be the halogen. Cut that from the tape. This needs to be a lithium. That's the precursor. And that's where the third step was. Why didn't you all say there is a third step? I looked at your notes. I approved them. I'm sorry. I'm sorry. And how do we get here? 2Li. Again, if you knew that the precursor to this was the organolithium, and you know that the organolithium's precursor is an organohalide, you could have gotten most of the points for this synthesis. You would have just been limited at this reagent. The other synthesis, it looked like a lot of you got this. Again, if I'm working backwards from my product, I know that I need to have an organolithium at that para position. And if I need to have an organolithium at that para position, that means I need to have an organohalide at that para position. And so to get an organohalide, here I'm doing EAS. I told you we'd leave orthopara and meta-directing in the EAS and NAS reactions. This is an EAS reaction. So you do need to realize how those groups affect the direction of the new substituent. Then 2Li, then copper iodine, half an equivalence, if you will. I do want to point out one alternative synthesis to this, which was first running Br2 with light, which gives you allylic halogenation. It doesn't consume the pi bond. It places the halogen on the terminal carbon in this case. Not in all cases, but in this molecule for sure. It places it there and only there. And then we can run reduction of the alkene, and we get the primary alkyl halide that we want. Again, 2Li to get us to the organolithium, and then copper iodide to get to the cuprate. I think that's more steps, right? 1, 2, 3, 4 instead of 3 steps. So it's not the most condensed, it's not the easiest synthesis, but it is absolutely a correct route, and I would give it full points. All right, when we come back on Thursday, we're going to look at reactions with organometallics in the 2 families, because again, they do different types of reactions. And then we're going to actually use that to segue into chemistry with alcohols. All right. Have a good night. I'll see you guys on Thursday.